easier to set up.
It is in fact, and it's also much lighter.
Yeah.
On the boundaries of whoops, that's the right thing. Right.
Perfection.
Gorgeous.
Perfection.
That's actually looking really good.
Yeah.
It's a very powerful decorator, very small body.
How did you get to afford this?
Donation?
I thought it was only a few thousand, 1 or 2 thousand.
It was like 1,300.
Oh. Okay. Yeah, I also wanted to ambush itself.
Oh, and I should also get the thing. The thing. Where's the thing?
Oh shoot. Also, how do we do trivia?
It's on here. Oh, we have to Barb's
Okay, cool. Sam no longer gonna come. I mean Megan.
Yeah, Megan is.
Oh no. What's that?
That's good? This works? Huh? Spoilers. I normally like to test the screen on my phone. My phone's dying. Oh no, I can test it. Yeah, I got you. Throne on Tap is now live. What are the odds? Oh, I forgot that this is now live. Is there some silly person like standing in front of the projector? There is now. Oh, good. Then we're not on much delay either. Yeah. I forgot that everything I say is now being recorded. That's why I announced that camera is now live streaming. I just instantly forgot. Something was out of you. Yep. Okay. Doing just fine. Yeah. I'm glad to be out here. Oh yeah, this is your. Oh, you were testing. Yeah. Hello. I'm not peeking. Surely I will not talk about it. Are you say some things? Yeah. It was going up and down. That's good. Cycle blocks? Do you have the clicker? I have a clicker. All the slides are here except for the second. Yes. So we'll just do a little switcheroo. Easy? Yeah. And I made the projector very perfect. Yeah. This is as good as the projector ever was. Yeah, this is definitely for what we sold. Yeah. And we're up to 1 viewer on this right here.
Nice.
Oh.
Who's talking this one?
Ed Lou.
Who?
Ed Lou. Oh, I should have added a slide for our.
I mean, not necessarily, but maybe. Ed Lou?
Is this food? I put it in the clothes, but I was confused.
Looking up food options ahead of time, and email it and like, so what about Wednesday? It's like, no, we're not. Yeah. But their website under events is real events, so that also got me.
Oh, really?
Yeah.
That's actually just remembered that we want you to come up here and get a trivia sheet from us instead, because there are more of you than of us. So if you want a trivia sheet, come up and grab one. Make sure you get a pencil. Start thinking about a team name. And we'll get started with the trivia in just a couple minutes. I saw the look on your face. What? Thank you. While you're all collecting your trivia sheets, I have a few quick announcements to make. First of all, I need to introduce myself in case you don't remember from last time. My name is Sam Charney. My name is Sam Charney, and I am a second-year graduate student at the University of Washington. Many of you may remember Megan, who was the previous head of Astronomy on Tap, and I took over for her, so if you have complaints, you can direct them to me now. I also wanted to thank you all profusely because we had a donation drive for the past couple months, and that let us purchase this beautiful projector. So thank you all so much. As you can see, it looks great, and it is really small, which is fantastic because we can take it to all sorts of places. Because last time we used was very large, and it sucked to bring. And also, I want to say this is our 100th Astronomy on Tap in Seattle. So thank you all so much for continuing to support us, continuing to come out and watch our talks and hang out with us. All right, I believe that is all my announcements. So now, actually I should announce briefly the speakers. You'll hear much more about them later and a little more about them from me later. But first up, we'll have Ryder Strauss talking about spinning asteroids, and then Ian Sullivan talking about exploring the changing night sky with the Rubin Observatory. Sounds very exciting. All right, I think I'm good. Did I miss anything? Nope. All right, I missed nothing. So now we're going to get started with the trivia. And I like hearing myself talk, so I'm going to read these questions out. So, question 1. What determines how fast a large asteroid can spin before breaking apart? Is it A, the temperature, B, the bulk density, C, the albedo, or D, the magnetic field? And I'll give you 30 seconds to think about it, discuss, and if you are giving a talk today, you should know the answers to some of these questions. I've been informed that this has been turned up. Is this louder?
No.
Should I turn it up more? I'm getting some yeses and some no's.
It's fine.
Okay. I'll talk a little bit louder. And if you can't hear, you can, sit close next to someone in a farther up row. That should be good. All right, it's been more than 30 seconds. You've had some more time to think. You should get it right now. Question 2. By measuring how an asteroid's brightness changes over time, astronomers can find its, is it A, orbital inclination, B, escape velocity, C, rotation period, or D, surface gravity? And also, as a quick reminder, you can check out our live stream on YouTube at the Astronomy on Top Seattle channel, and you can also look at the trivia questions on there if you're having trouble seeing them from your location. All right, question 3. Which is the most common asteroid type in the asteroid main belt? Is it A, stony, S-type, B, carbonaceous, C-type, C, metallic, M-type, or D, dark outer belt, D-type? I bet you can't guess where the type letters come from. And after I run through them once, I'll do them again, but faster, just in case you need some last-minute thinking time. All right, question 4. What feature makes a comet different from an asteroid? Is it A, it orbits the sun, B, it has moons, C, it can have a coma, or D, it has a density greater than 3 grams per cubic centimeter? It's our first number on the trivia today.
Two numbers in one.
That's true, but it's the same one twice. One of them's just small. Question 5. Which planet hosts the Trojan asteroids in its orbit? Is it A, Earth, B, Mars, C, Jupiter, or D, Mercury? Question 6. Which of these is not a transient event Rubin will track? Is it A, supernovae, B, gamma ray burst, C, planetary transit, or D, stellar parallax? Which of these is not a transient event Rubin will track? Our speakers are stumped, which is not a good sign for the rest of you. Question 7. About how many real-time alerts will Rubin Observatory generate each night? A, hundreds, B, thousands, C, 10 million, approximately, or D, over 1 billion? Now, I would say this is more numbers, but it's just ones and zeros. Question 8. Rubin's real-time alerts will help coordinate with other telescopes to catch fast events like A, solar flares, B, neutrino bursts, C, quasar activity, or D, tidal waves. It's a good thing I don't have to know the answers to these. Question 9. The Rubin Observatory's camera has how many pixels? Is it A, 320 million, B, 1.2 billion, C, 3.2 billion, or D, 12 billion? These are all really big numbers. I heard someone say a lot. That is really correct. All these numbers are large. I win! Yeah! All right, and last up, which of these cosmic events is an example of a time domain target Rubin will observe? A, galaxy cluster lensing, B, expansion of the universe, C, type 1a supernova explosion, or D, the cosmic microwave background? Which of these is a time domain target Rubin will observe? All right, now I'm going to go back to the start and go through them again, but this time faster. And I'm not going to read them this time because I can't read as fast. So I'll have about 15 seconds per slide just to finalize your thoughts.
if you feel confident in your answers and you don't feel like you need to get this second round, you can come and bring them up now. But otherwise, you're free to wait until after this, and we'll look at them and grade you while the talks are going on, and we'll get back to the answers after the first talk. Make sure you've written a team name of some description on top so that we can identify you when the time comes.
You always told me standardized tests. Never
I don't think
never turn it around.
this was not standardized.
Thank you very much. It's a lot of seeds. Were there a lot of seeds?
You know, beans and seeds. Not as typical DJs would have had once. That's been too easy.
I worry that a couple of these might be ambiguous. The couple where I
I
have two
know.
answers. You like that?
Yeah,
You like some ambiguous?
I know. Yeah, some definitely able to.
Yeah. Would you ever consider making two answers correct? Like, like you put in the answer field, see if
Yeah, that's big.
you don't like it. You don't like it.
So, I remember the high school.
We used to have one or two possible questions.
What do you meant possible?
Like most of the messages, of course, it could be one now.
Yeah. No, I think it would be good too.
I like all the questions. There's a couple answers that are suspicious.
But there's one more right that I don't want to do.
Okay.
All right, that is time for trivia. Please come up and bring us your trivia sheets so that we can grade them. And now we're going to go transition to our first talk. To give us a couple minutes.
Are you supposed to talk about this? Ooh, like Jake.
Oh, I bet this black button makes it black. Let's get that into a slide at the end before we announce it. Oh, I think we can get a QR code.
Yeah, okay, cool. Thanks, guys.
Yeah. Thank you. Whoops.
Very unprofessional.
No.
How can we know that you were using slides? And then you're showing the moon hitting the earth.
Whoop. Those big events go 10-kilometer factor. Sun goes supernova.
That's a good one. Will we see? There's nothing to prevent.
All right, everyone. The time has come for our first talk of the night. It is my great pleasure to introduce Ryder Strauss, who is a current postdoctoral scholar at the University of Washington, and who very recently got his doctorate from the Northern Arizona University. So this is Dr. Ryder Strauss. And he's going to tell you all about asteroids and spin, not the physics kind, different kind.
Thank you, Sam. Oh, my clicker. Amazing. Can you hear me okay? Yeah. Awesome. Hi, everyone. Thanks so much for coming out. I'm excited to be here. Yeah, as Sam said, my name is Ryder. I am a very, very brand new postdoc here at the University of Washington Astronomy Department. And yeah, today I'm going to be speaking a little bit about some of my research I've done involving examining the rotation characteristics of spinning asteroids. There's a lot of work that made up my PhD.
Sorry, hold on. I'm trying to make
And we're standing by.
and it's not doing it again. Why is it only sometimes? Oh, that's... All right, go for it.
Hey, amazing. So a brief introduction. Who am I? Where do I come from? I got my Bachelor's of Arts in Astronomy at the University of Colorado in Boulder. That's where I was born. And then I headed down to Arizona, Flagstaff, Arizona, where I got my master's and PhD in astronomy and planetary science. At Northern Arizona University, I studied under Dr. David Trilling. And yeah, I'm excited to be here. I've just started my astronomy postdoc here at the University of Washington. It's my first time in the Pacific Northwest. And as you can see at the bottom, I have been blessed and fortunate to always live in places with forests and mountains. And I'm very excited to engage with some brand new forests and mountains up here. Oh yeah, and when I'm not doing astronomy, I do love hiking, I love board games, I love canoeing, rock climbing. I'm a big movie buff, and I'm a big animal lover, cats and dogs. Okay, so first, a brief overview of this talk. So I'm going to start off by giving a brief introduction to minor planets, a little tour of the solar system, and what are the different populations of small objects in the solar system. I'm then going to give an introduction to some photometry techniques and light curves. We're going to talk about what is a light curve and how can we use light curves to do interesting science on asteroids. Then I'm going to talk about the observational survey that made up the bulk of my PhD project, which is the Decam Ecliptic Exploration Project, called DEEP for short. And I'm going to detail, I'm going to introduce it, and then I'm going to detail three sort of main asteroid light curve projects that I've undertaken with the DEEP data set. And then I'm going to very briefly touch on where do we go from here now that I'm at UW, no longer working on this PhD research project. Where do I take these thing asteroids into the future? So let's get started with the solar system. These are our familiar friends. The biggest objects in the solar system dominate the mass of the solar system. Primarily, the mass of the solar system is stored in the sun, and then after that, most of the solar system's mass is stored amongst the 8 major planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Because I did my PhD in Flagstaff, Arizona, where Pluto was discovered, I can tell you definitively I don't think Pluto is a planet. But that doesn't matter because Pluto's a dwarf planet, and that's what I study. So in terms of numbers, the major planets are actually not the dominant population in the solar system. They're completely dwarfed by what we call minor planets, or the small subplanetary bodies orbiting the sun. This is just an animation that I stole from JPL Horizons of, just an orbital integration of all of the known main belt asteroids in their orbits around the inner solar system. You see the Sun, Mercury, Venus, and Earth, and Mars marked there. Okay, so minor planets can be further broken down into several different populations. They're found sort of all over the solar system. And so here we'll focus on a couple of different individual primary dynamical populations. There are what we call near-Earth objects. These are rocky bodies that come very close to Earth's orbit. These are interesting for both sample collections and spacecraft encounters, but also because these can be potentially hazardous objects and have a planetary defense interest to us. There are main belt asteroids. These are probably the most numerous and well-known of the minor planets these days. These are the rocky bodies that largely orbit in the main belt between Mars and Jupiter. Then we have the trans-Neptunian objects. These are, or TNOs for short, and these are sort of the most distant objects in our solar system. These are these icy bodies that orbit outside of the orbit of Neptune. That's why we call them trans-Neptunian. And then there's this sort of weird transient population called centaurs, which are not quite trans-Neptunian objects. So in this figure of the outer solar system here, you can see Jupiter, Saturn, Uranus, and Neptune. And these blue guys are all of our trans-Neptunian outer solar system objects. And the sort of dispersed green guys are the centaurs. These are asteroids that orbit within the orbits of the giant planets. And because of this, they're a pretty young and dynamically active, unstable population. Okay, a little more on near-Earth objects. These are objects that have perihelion. This is how close do they come to the sun, of less than 1.3 AU. They're very small. They're very fast-moving because when we fly by them by the Earth and observe them with a telescope, the Earth is moving really, really quickly by these fast-moving close-by objects, and so they appear as very elongated streaks in our images. They're easy to access via spacecraft because they're so nearby, and that's why we've done so many sample return missions with the DART and Hayabusa sample return missions. Or I guess DART wasn't a sample return, that was a asteroid redirect test mission. The OSIRIS-REx and Hayabusa sample return missions. That's why we chose a near-Earth asteroid for the DART redirect test, because they're really near to us. They're easy to get to. But because they're close to us, a lot of them are potentially hazardous. So there's sort of a love-hate relationship with the near-Earth objects amongst astronomers. But they are believed to originate from the main belt. They're believed to be main belters that have, by some mechanism, migrated inwards to the inner solar system. And then the trans-Neptunian objects, these are the most distant objects. They're sort of the little brothers and sisters of Pluto. And this is actually Pluto to the left here. I say Pluto isn't a planet because there are about 5,000 of these guys that are very similar to Pluto that are known to us. And a lot of them are even bigger and or more massive than Pluto. So if we were to refer to Pluto as a planet, then we would have to have our elementary schoolers memorize. Oh, thank you. Oh no. Oh no. Yay! Yeah, I didn't like what I said about Pluto. I stand by it. I want our elementary schoolers memorizing 40 planets, or I want them memorizing 8 planets and not 40 planets. And if we called Pluto a planet, that's what we would have to do. I've talked about centaurs already. There's these dynamically unstable objects that orbit between the giant planets, and because they're so unstable, because of their gravitational interactions with Jupiter, Uranus, Neptune, Saturn, they're thought to be examples of outer solar system TNO material actively migrating inwards to become a Jupiter family comet. Together, the minor planets are my favorite group of solar system objects. They provide a really comprehensive map of the entire solar system. Because there are so many of them, there are more than 1 million that are known to us right now. We can do some really powerful statistics on them. Because they're so small relative to the giant planets, we can treat them as gravitational test particles to track the gravitational and orbital history of the big planets, like Jupiter's migration. And they sort of provide this compositional map of both the present and past solar system. They're spread all over, and we can observe a whole bunch of them. And particularly interesting to me is I think these small bodies are a likely mechanism for the transport of volatiles. So I think it's likely that early on in the early solar system, a lot of ices and hydrocarbons and things that might have been too volatile to naturally accrete in where the Earth is in this habitable region. The small bodies that accreted farther out in the solar system and were able to collect these more complex organic materials were subsequently able to deliver that material inwards to Earth and give us life. And that's pretty neat. So minor planets are really interesting to study, but because for a lot of the same reasons that they're valuable to study, they can also be really hard to study. So because there are so many of them, and they're so diverse, it can be really hard to try and do like a spacecraft encounter to every single asteroid, because there's millions, and spacecraft encounters are expensive. They're also largely too small and faint to resolve from Earth. We can't photograph an asteroid and measure what is that asteroid's shape. All it looks to us is a single infinitesimally small point of light. So from the ground, we're sort of limited to measuring a single parameter. We're counting the photons reaching us from an asteroid. We call this photometry. And this is the bulk of my research interest, is inspecting what we can learn about these asteroids from their photometry and how their photometry varies in time. So here's an asteroid. I believe this is a near-Earth object, Eros. As an asteroid rotates over time, you can sort of see in this animation, its projected cross-section, how much of it you see on the sky, changes periodically, right? It's bigger, then it looks smaller, now it looks bigger, now it looks smaller. This will manifest as a periodic variation in brightness. So even though we might not be able to actually, this is from a spacecraft flyby, even if from the ground we might not be able to actually observe this video of the changing shape, we can measure the variation of brightness as a function of time, which is this figure on the right here. And we can learn a lot about this object's rotational state. We can learn its rotation period from the period of the light curve. We can learn its approximate shape from the amplitude of the light curve. And depending on how much photometric precision we have on this data, we can even learn more detailed things about the object's shape, up to, is it a single body or is it a binary? So these light curves are really, really powerful tools because we're adding this time dimension to our basic collection of photons. Okay, so that's one object. There are a lot of objects, so we need some large-scale, wide-field ground-based surveys to measure light curves of many, many, many minor planets at the same time. And this is where we come to the Decam Ecliptic Exploration Project, which was my PhD project. This project used a dark energy camera, which at the time of its construction was the biggest camera that humans have ever made. It's mounted on a telescope down in Chile, and it gives us this particularly uniquely wide field of view, high sensitivity, and with the survey, we observe at a very fast cadence with this 2-minute time resolution, so we're sensitive to very short-term variation in the asteroid's brightness. And then here is me when I got to visit the Decam. It is up there, and that is me as an astronomer for scale. Okay, so DEEP was originally conceived as a TNO discovery survey. So we were gonna search through these really, really faint subthreshold data and do some digital tracking and moving of our images on top of each other until we find these really bright points, which are confirmed discoveries of trans-Neptunian objects. But the brightest objects in the DEEP data set don't actually need this multiple exposure tracking approach that we've been doing, because each individual image is so sensitive on its own. With this DEEP survey, we were able to collect really fast cadence light curves for thousands of main belt asteroids. I think we got like 60,000 main belt asteroids in this data set. We got about 100 TNOs in our data set. And most of these TNOs have have diameters smaller than 100 kilometers, which are relatively rare in the literature because DEEP is sort of, to date, the biggest wide field survey of its kind. And then, there are in the literature photometry and light curves for hundreds of thousands of these main belt asteroids, but not with our combination of cadence and sensitivity. So DEEP is uniquely equipped to measure short-term variability, and it's sensitive to a unique brightness regime and size regime in these solar system populations that we're looking at. So I'll briefly go through three sort of science results from these light curve studies that we've done with asteroids from the DEEP survey. So I'm going to start with, I think, the most interesting, and these are the super fast rotating asteroids. So the title of my talk is Spinning Asteroids. These are the asteroids that are spinning the most. Oh no. I got these slides out of order. Light curves of super fast rotating asteroids. I'm going to start with the super fast rotating asteroids. Okay. I stole these slides largely from my dissertation defense, so some stuff was left over. Okay, let's talk about super fast rotating asteroids because they're very interesting to me, and they're this really interesting tool to probe the interior structure of asteroids using just ground-based photometry. So what we're looking at right here is a figure. This is from the Asteroid Light Curve Database, which is a publicly available online database of asteroids with published light curves. And on the bottom axis, we have diameter in kilometers. And on the vertical axis, we have period, rotation period in hours. And you can see I've marked in red this quote-unquote spin barrier at about 2.2 hours, where we empirically see this really dramatic drop-off in the number of asteroids that have rotation periods shorter than 2.2 hours. A lot of asteroids with rotation periods longer than 2.2 hours, but something happens at 2.2 hours that just sort of seems to prohibit asteroids from falling into this region. You can see there are a couple of spots that are above this dashed line. This is a particularly interesting and unique group of asteroids called superfast rotators. Basically, the reason for this is centrifugal force, right? You spin a bucket full of water and the water stays in the bucket. If you spin that bucket fast enough, the rope will break and the water is going to fly everywhere. And these super fast rotators are asteroids that their water should have flown everywhere and it hasn't, and that's very confusing. So that implies that there's got to be some kind of significant cohesive strength holding them together. That's pretty weird because we think of asteroids as being these kind of dry, rocky piles of rubble and gravel sort of held together by gravity. So the presence of some extra significant stickiness is kind of surprising. And it just so happens that this DEEP survey has the perfect cadence to measure super fast rotators. So here in magenta, I've indicated where in this parameter space the DEEP survey was sensitive to. Because we have this big telescope, because we were observing at this very fast time cadence, we're sensitive to really short period variations and short period variations for pretty small objects. And we found a couple. So in a search of about 700 asteroid light curves from one night of our survey data set, we found 3 superfast rotators that we were able to confirm their rotation periods. 2 of them had close to 12-minute rotation periods, and one had a close to 40-minute rotation period. Both of those rotation periods are well below that 2.2-hour spin barrier. I will also note that, as we perhaps saw in our trivia question early on, that the location of the spin barrier is dependent on the bulk density of the population that you're looking at. So the fact that this entire population seems to fall in the same region and have this spin barrier of 2.2 hours, that's actually kind of a decent measurement of the bulk population of the asteroids that are represented within this data set. Okay, so with the survey, we found these super fast rotators, these asteroids that should be flinging themselves apart. They haven't flung themselves apart. What can we do with these? Well, it turns out that because we know how fast they have to be rotating to, in theory, fling themselves apart, we can do the physics to equate the gravitational force experienced by like regolith on their surface, pebbles on their surfaces, to the centrifugal force experienced, and we can determine what exactly the required cohesive strength in pascals is for these super fast rotators. And so this is a figure for one of these three objects. Got the required cohesive strength on the y-axis, the bulk density on the x-axis. And you can see that for basically any physically reasonable bulk density, this object requires a considerable cohesive strength internally to exist and to exist with the rotational characteristics that we've measured. So this is really exciting, and because I'm a little tight on time, I'm gonna skip through a bunch of my other slides and talk about, like, yeah, this is a really exciting method by which we're probing the interior physics. What is going on inside of these asteroids that is holding them together just by counting how many photons are bouncing off of the sun and hitting our telescopes. So what comes next? Well, those of you who are familiar with lots of the astronomy that goes on here at UW may note that there's a huge elephant in the room that I've not yet once mentioned, and that is LSST. So DECAM, the camera that I built my entire PhD around, is no longer the largest camera in the world. Very recently, that mantle was passed over to the Legacy Survey of Space and Time, or LSST camera, which is mounted at the Vera Rubin Observatory down in Chile. Actually, just the next mountain over from where DECAM is. I visited DECAM and I could see LSST from the next mountain over. LSST is a way bigger telescope than the telescope that DECAM is mounted on. It's got a way bigger camera, way more pixels, way bigger focal plane. And they're talking about discovering as many as 1 million asteroids just in the first year of the survey. More than 1 million. Jake is telling me more than 1 million. 2 million. Oh my goodness. Oh my goodness. That's a new figure. I said more than 1 million, so I got it right, but that's amazing. More than 2 million asteroids are going to be discovered in the first year of the survey. That's equivalent to the number of asteroids that are known to humans, period. So in the first year, LSST is going to double sort of the number of asteroids that we know about. And with all of these comes a lot of similar science to DEEP. We've got these deep drilling fields that are going to replicate the long stare observing cadence as DEEP. And then LSST is going to cover a whole bunch more of the sky than DEEP. And it's gonna, I think, provide a more powerful ability to do larger statistics across the whole sky. And I think the last point I have is LSST has colors. The DEEP survey did not have colors, so we will be able to do all of the same science we've done with DEEP, but we will be able to add the addition of colors, which will allow us to hopefully differentiate between more of these things like S-types and C-type asteroids and whatnot in our data. Yeah, light curves are an amazing tool for measuring asteroids, and I'm excited that as our capabilities continue to grow, our ability to study these asteroids is going to continue to grow. And that is all I have. This is my email down at the bottom. Thank you so much. Yes, yeah.
So
So you left us at a cliffhanger. So why was the asteroid not spinning itself apart?
Why was the asteroid not spinning itself apart?
Was it full of gold?
Was it full of gold? Was it full of gold? We don't think so. So our best guess is that most of these asteroids are S-types, and they've got a largely relatively uniform density, and certainly within a factor of 2 or 4. I think the densities of these guys are relatively uniform. I think rather than really heavy stuff increasing the gravitational force holding these asteroids together, I think it is effects of I think it's actually effects of the particle size of the regolith within these asteroids. So we think of most asteroids as not sort of solid monoliths, but as rubble piles of gravitationally bound material. And it turns out that if you make this material small enough, you get these situations. And we see this with the way the footprints on the moon landing are so perfectly preserved on that lunar regolith. Really, really fine material has a lot of electrostatic forces that bind it together. That's why it's easier to build a sand castle with fine sand than it is to build a sand castle with gravel. And so my favorite hypothesis is I think with these super fast rotators, we're actually looking at asteroids that have really, really fine material in their interiors. And that's contributing to a really, really significant, we call it van der Waals electrostatic attraction in the interior. I think the sexier answer that I like to imagine is all of these asteroids are actually full of ice and volatiles and hydrocarbons and water and life-making chemicals, and they are cementing the wet sand of the asteroids together in a snowball. Yes, in the hoodie.
One of the big news things from the first round of LSST stuff was they found a bunch of new asteroids. So, is there anything that you can just speak to about that? Like, are you doing anything with that, or just...
I can speak to, I have not done anything with that data yet. I haven't gotten my hands on that data, but that is in the pipeline. And one of my big goals, having moved here, is to start, getting my mitts into some of that data and trying to do some of the science with that new data.
Most asteroids are shown as very lumpy. The object former planet known as Pluto is round, and some of the trans-Neptune objects are round. Is it understood what's the transition between a lumpy asteroid and a spherical object? Do you understand that?
Yeah. So that's basically a size transition, and that's actually pretty closely related to this internal gravitational versus cohesive strength argument. So what you can do is you can draw an equivalency between the hydrostatic force. No, I'm explaining this wrong. There are two different size regimes in a situation where you have something like a big old pile of rock being held together gravitationally. You sort of have two different size regimes, and these super fast rotators kind of dictate where are we interested in these size regimes. So the larger objects, we call them gravitationally bound because this cohesive strength effect is not dependent on size, right? If you're thinking about particles sticking themselves together with electrostatic forces, those aren't going to care if they're a bunch of particles or a few particles. But as you make an object larger, the gravitational force experienced by particles in that object is going to significantly increase. And so eventually you cross over into this size regime where you can picture it like the forces required to hold Mount Everest up are surpassed. If you make Earth massive enough, the forces required to hold Mount Everest up in the sky are surpassed by the gravitational force dragging Mount Everest down to the Earth. And so for the largest small solar system objects, largest solar system objects, we see these with the planets too, and even with the largest main belt asteroids like Ceres and Vesta, we do see this sort of natural settling into sphericity because they are dominated by gravity rather than dominated by other forces within the material. Does that make sense?
Is there a threshold, a known threshold?
Is there a known threshold? The sort of 100-kilometer size range-ish is what I've seen. Sort of, we see a lot of 500-kilometer, 1,000-kilometer, very round Pluto-like objects, but down below 100 kilometers, we start to see lumpier things. Yeah.
Have to not fuck this up. I think I instantly fucked it up. All right. So before our brief intermission and our next speaker gives a talk, we are going to go over the trivia answers. While we are still on this computer, we'll skip past all of these. So I'm gonna, very quickly, these were the questions. Wow, questions. Wow, yeah, these were some tough questions. All right, so the trivia answers are the first question: the bulk density determines how fast a large asteroid can spin before breaking apart. As we heard, the rotation period of an asteroid determines its... You can find its rotation period via looking at its brightness. This one is C. Question 3 is B, carbonaceous or C type. Question 4 is it can show a coma, or it's C. Question 5 is C, Jupiter. Got a lot of C's in a row here. Question 6 is D, stellar parallax. And now we're getting into some mild spoiler trivia questions for the next talk. Question 7 is C, about 10 million alerts per night. Question 8. Yes.
Won't that go down over time?
That is a good question that you should ask someone who's not me. Yeah, hold that thought. Question 8 is B, neutrino bursts, which will be very cool. Question 9, the camera has 3.2 billion pixels in it. It's a lot of pixels. The favorite analogy that Mario Jurich likes to use is that it would take 440 basketball courts in a square to be big enough to hold one picture of Rubin. Is that wrong? Jake is squinting at me, so I might have said it wrong, but it's something like that. It's a lot of basketball courts. It's a really big picture. And question 10, it is C, type 1a supernova explosion is an example of a time domain target. Yes. And in perhaps unprecedentedly, well, maybe not, we have someone who got 9 of them right on the trivia, which is very impressive. Now, I will remind you that if you are one of the speakers, that you can come talk to us for prizes later, but you don't get trivia prizes. But if we call your name during intermission, please come up and talk to us and grab a prize for your very intelligent trivia answers. So we had 3 teams that got 8 of them right, so we'll start with those teams. We have team, or perhaps not team, Rob Solo. Good job. Were you in fact solo?
Yeah.
All right, nice. We have Team Cloudy Skies. And also with 8, we have Team Haliens. Haliens. I see. Nice. And with 9, a whopping 9 points, is Team. Woo! Very impressive. And also, since not trivia related, remember if you are one of these teams, come up, talk to us, get your prizes. Since we have the UW does multiple types of outreach events, and we like to support each other. So if you are affiliated with the University of Washington and are interested in tutoring children who are incarcerated, please raise your hand and we'll get you a flyer. You unfortunately do have to be affiliated with the university. So if you're not, then we can't help you. But there's a program called eSteam, and it's a fantastic program. Jake, does that include alumni? He doesn't think so. But it is an incredible program, and we'd love to get as many people as possible to help out with it so that we can help teach as many students as possible. And with that, congratulations to our trivia winners. We'll take a brief intermission before our next speaker. Thanks, everyone.
Is that RSL?
Okay. Right. We do have to wait for this guy to.
Yeah.
Can I get you to continue your question on the other side so that we have the projector? Thank you. All right. Welcome back, everyone, from the intermission. I hope you all had a very restful 10 minutes. And next up, I am very happy to introduce Dr. Ian Sullivan, who is currently a research scientist at the University of Washington and works at the sort of intersection of astronomy and data science, came to us from NASA and helps to work on the Rubin Observatory and how to deal with very large data products. Give him a hand, everyone.
Thank you very much. And thank you to Ryder for the nice introduction to this talk, because now I'm mostly going to talk about the Rubin Observatory and what we are doing with, I'm going to focus on more of what we locally at UW work on. So I'm going to focus on some of the asteroids and transient and variable science, and get to ways that amateur scientists can get involved. Let me get my little clicker out. So just to set the stage, earlier this year we released our first public images from Rubin, where we had taken a special survey where we were working in a slightly different mode to get the high image quality early on before we had everything really automated, and put together these beautiful full color images that are available, and you can go and you can zoom around and see all kinds of neat things in them. And there's just a lot of neat stuff you can see in these different images. This one's, you're seeing the little colorful streaks of asteroids as they move through, and the different colors are when it was observed with different filters. These are the, we have colors now. Appreciate that. This is from one of our not too long ago observing nights, when one of the observers noticed that they could get a shot of a comet right above the observatory there, and they just ran out and snapped a shot of the observatory at night, and this was my desktop wallpaper for a long time. So, I think it's important to mention that we're the Vera Rubin Observatory, and we're named after a pioneering dark matter scientist, Dr. Vera Rubin, who was the person who conclusively proved the existence of dark matter by studying the rotation curves of galaxies. And the Rubin Observatory is the first major observatory named for a woman. But in addition to that, we have a quarter, a US quarter. They're real things. Maybe you'll get one in change sometime if you still get physical change. Otherwise, you could be a nerd like me and order them from the US Mint. So, but I'm excited about that because I've never been part of a project that was on our money before. So, where is the Rubin Observatory? And in this, if that angle was shifted a little bit over, you would have been able to see where DCAM is situated. So we are in Chile, which is nearest the city of La Serena, which is about an hour flight north of Santiago, which is probably the place that you've heard about in Chile. La Serena is on the beach. It's a nice place. And then you can take a bus for about 2 hours up into the mountains, going up some really sketchy roads to the summit here, where there's actually a few observatories. We have the Rubin Observatory, we have another little telescope that we use for atmospheric monitoring, and then we have a few other telescopes just off to the side. And it's an interesting place to be. So, another view of that, we heard a little bit of the specs of Rubin Observatory, so I'll go a little bit fast over that. But the really important figure from all of this is this funny word, étendue. So, but it's important. It's what sets Rubin Observatory apart from anything else. So it is the combination of wide field of view and high resolution. our resolution is at 0.2 arc seconds, which most people don't have that much of a sense of what is 0.2 arc seconds, but the James Webb Space Telescope has resolution just a bit better than that, but our field of view is 10,000 times bigger. This allows us to image the entire sky at the resolution almost of a space telescope every 3 days. And that means that we can build up a movie. And I'll get to this later, but what really sets this apart is that because you have then taken this high-resolution image of the entire night sky, what really is groundbreaking is that when an event happens, you will have already taken detailed imaging and photometry of that object before the interesting event happened. So it's like you can go back in time and see what was happening in the vicinity of the supernova or the other event. And you will have that detailed imaging from the past because we're just making these images all the time. Our first images, the ones that I was showing here, were taken just this April. And this week, we have finally shut down for our first engineering shutdown while we do a bit of work on our camera system. This was planned, and put in a little bit more light baffling to improve the stray light performance. And in about a month, we'll come back, finish up our commissioning, and by the end of the year, we should be streaming alerts to the world. We'll see. So another thing that I find fascinating about the Rubin Observatory is anyone here an amateur photographer? Not too many people, but I got interested in amateur photography and have my different lenses to see the, lens size and the, all of a sudden, very basic things are just vanishing out of my head. The focal ratio of the, apologies, blanked on the amateur astronomy stuff here, but the focal ratio of the Rubin is about 1.2 for a 8-meter telescope. And so if you often think of a very common lens for a nice professional camera might be, a 50 millimeter, f1.4 lens. And this is now extrapolate that out to 8.4 meters. It is so much more collecting area. And to build an optical system that can have a good image quality across a focal plane that is literally this big. It is as big as a table at a bar, bigger than mini bars, in fact. And to have good optical quality across that entire table is really impressive. And that is something that drove a lot of the design considerations of the observatory, but it was all necessary for what we were then going to be able to do with it. If you are able to visit the observatory, this was a little while ago while we were still under construction, my one visit there so far, but again, for scale, that is the structure there. We don't have the mirror on it yet, but the entire thing is about, well, that structure there is about 6 stories tall, with a few stories, with about 2 stories below us that you can't see, that are all part of the rotation part of the mount, that are the big oil well, that it floats on a bed of oil, and then has huge cable wraps that descend for an entire story and look like something out of a sci-fi movie. Something like the Dr. Octopus is going to get you sort of thing. And this whole thing is built so that, and this is real time, this entire mini-ton multi-story machine moves. This is moving 6 degrees a second right now. And this is up on a mountaintop. This is having to be powered by batteries supplied by commercial power and a giant capacitor bank that fills with 1.4 gigawatts of power in the capacitors and drives that and uses a lot of that power and then regenerates it with regenerative braking as it slows down. It is a massive amount of power to move a thing this big and so smoothly, because we have to immediately take images again at high resolution as soon as it has finished moving. Seen on the back, the yellow thing is the mass simulator that is equivalent to the mass of the mirror so that we could do these early tests. So this is a combination of a number of factors in order to build a unique instrument. We have our wide field of view, the speed, and the large mirror is what makes it possible to see faint objects. And those combined give us power to see an incredible amount of different science. It was built with 4 science drivers in mind. I'm going to mostly talk for the rest of the time about the 2 things on the right, but that's not to say that there aren't a lot of people interested on the things on the left. We can really probe dark matter and the nature of dark matter and dark energy. That's what the work Vera Rubin did, and that people are continuing to work on, especially with dark energy, where we're going to have to try to see faint statistical structures throughout the entire southern sky in order to statistically determine properties of dark energy. The study of weak lensing, which is one of those things that sounds really complicated and is. We'll also be mapping the Milky Way. We live in a galaxy. We see pictures of the galaxy all the time, but it is a bit of an open question of what does our galaxy actually look like? Like, how many spiral arms are there in the Milky Way? We can't see it because we're in it. But the more we map it out, the better an idea we can get of what our galaxy looks like. On the solar system, we've heard a fair bit already. I will tell you a little bit about what Rubin is going to do and what we have done as well. And I'll tell you a bit about the transients as well. But first, why does it move so fast? Well, we're trying to map out this entire sky every 3 nights. And that is 18,000 degrees, 18,000 square degrees, I should say, that we are trying to map to this 0.2 arcsecond resolution. That is a lot of images. That's a lot of pixels. This is what, if you watch this little dot, this is what a simulation of our observing looks like for 1 night as it begins to zoom around. When it changes colors, that's us changing the filters. Inside the cryostat, we have a filter changer that allows us to bring in essentially not different lenses, but different filters that will block everything except the appropriate wavelengths of light. And so we can change in about 5 minutes what wavelengths of light we are looking at. And over time, build up this whole mapping that is then getting many different colors. You'll see it hover for a little while in certain places. That's because we also do what we call these deep drilling fields, where we're going to really observe in detail over and over again a few fields that have been covered by other experiments in the past, and we want to have a good long history, and we can get other science from having a rapid cadence of observations within those fields. So as we're looking for the things that change, this was in the trivia. We're expecting to see around 10 million changes per night. That is what me and my group work on at UW, is trying to figure out the data pipeline of this is a lot of data that is coming through each night. This is about 10 terabytes of images, and we have to reduce those to something resembling science, ideally within 2 minutes or less after the shutter closes on the mountain. This is not how most observatories have worked in the past. Usually there is some amount of time of processing, and there are some that will, like ZTF, which will release their alerts within 10 or 15 minutes. we are aiming for less than 2 minutes. And we are almost hitting that. But what this can also let us do is that with so much data, those really rare events will be relatively common. If you're looking for a 1 in a million event, if you've observed billions and billions of objects, you've got a bunch of those 1 in a million events in there. So then the challenge is identifying those interesting events out of all of your observations. And this is where the big data part of it comes in, where we have to really plumb the data and get many scientists around the world engaged, looking at the results and finding those interesting events. Have one quick animation of some of our early results from around April. These were released publicly, but this is zooming in on that deep image we had at first. And that is the level of detail that these have. The different colors here are because we observed in those different filters. And here we can see one star that we observe multiple times, and at different times, it has different brightnesses. As we then zoom to another region of the sky, well, we can follow the light curves of some of the other stars. And these small changes in brightness are sufficient to do quite a bit of science. You can study these light curves of all these different stars. These then are being shown are all our Lyrae stars that have a very predictable pattern to their light curves. And so we were able to measure that earlier this year for all of those. There were many of them highlighted there at the very end. I guess I should have frozen this not on the Vera Rubin observatory frame, but on the final slide. Sorry about that. So those ones we highlighted at first because they're easy to pick out, because they have predictable patterns, and so we can say, we know this is a real variable, we know this is real science, it's safe to show. There will be a lot more coming once we're not trying to just focus on the safe science at first, because we have to we have to show that the whole thing works first before we get on to things that are really exciting. On solar system, and a lot of this work is done by Jake here, actually. So thank you, Jake. Who was telling us earlier during Ryder's talk about the millions of asteroids that we are going to be detecting starting in the first year. And we already are. Unofficially, we are detecting a lot of asteroids. I think it's safe to say that without breaking anything. And very soon, we should be able to release those detections to the Minot Planet Center and have that be public knowledge. And we are working on that. I would like to highlight one thing from that, in fact, using the Vera Rubin quarters. So it seems like the uncertainties in our positions are around 5 milliarcseconds on these asteroids. Now, the Vera Rubin quarter I have in my hand is 1 inch across. I'd like to ask the crowd, and whoever gets the closest answer gets this quarter. So how far away would you need to be for this quarter to appear to be 5 milliarcseconds? No calculators, no phones.
8 miles.
I heard 8 miles, I heard 2 football fields.
4 miles.
Other guesses?
10 miles.
11 billion furlongs.
I can't calculate that in my head. I don't. Okay, I hear 17,000 miles. I hear Sacramento. All right, that's a lot, especially because Sacramento is really close. It is actually almost precisely 1,000 miles away you would need to be for this to appear 5 milliarcseconds across. Who said the? Come on up. Congratulations. So I find it can be hard to appreciate just how small 5 milliarcseconds is. But also remember that our pixels are 0.2 arcseconds. So this is 1/40th of a pixel. And that's pretty good for the overall accuracy of the positions of the objects that we're able to calculate with this. All of that is a little bit preliminary, but no, we're feeling pretty good about those numbers. So we've seen a bunch of these asteroids. Got one more little movie. Zooming in on detection of an asteroid and watching as that moves across, and we can see these move all over the place. So these are from our first look data set, of which we released a large number of asteroids. How many did we actually have in that? 2,000? Yeah, so 2,000 asteroids in that very first. Here they're colored by the type of asteroid they are. Most of these mean main belt asteroids and a few of the Trojans. And that's just one small slice of what we could see in the entire solar system, because this was just from a couple days. And you can imagine what that's going to be like once we have been observing for a whole year and observing that entire slice of the solar system. And I'm impressed how well it works, and thanks, Jake. A further simulation of that that is showing the types of detections that we would be expecting to see of the main belt here in yellow, the Centaurs in orange, and the Trojans in pink. Yeah, and then some trans-Neptunian objects like Pluto's out here in the deep blues, out in the distance. So we could easily expect to find the greater than 1 million of these objects in the first year, hopefully with that clock starting very soon. But we can also find more rare things like interstellar objects, of which up to a couple months ago, there'd only ever been 2 seen. And luckily, Rubin happened to be pointing at approximately the right place, and with just a few tweaks and some phone call, well, okay, Slack messages to someone who was at the control room, we could nudge the telescope over a little bit and just happen to get some science out of our focusing tests. So here we have an image of the interstellar comet 3I Atlas, named because it was first detected by Atlas. And the image was put together by people in UW. Many people contributed to that. I had a small part in that, but many other people worked on that. And taken together, even had a nice little movie of the comet moving through. I think Colin put this one together. So as a final thing that was not in the science interests, the Rubin Observatory has a special role for the US. Some time back, Congress mandated that NASA fund something that could detect any asteroids that could impact and imperil the Earth. They didn't say what it would be. They're like, figure it out. And what that thing is the Rubin Observatory, because Rubin can catalog everything and find the things that are unusual. Because the problem with the things that could imperil the Earth is that they're small compared to a planet, and they'd be moving fast, so you wouldn't tend to see them with a pointed observation of different telescopes. However, with something like Rubin, where you are imaging the entire sky frequently in high resolution, and you can piece together all of those orbits, with the work that we're doing at UW, we can actually piece together that into orbits and calculate the probability of it impacting the Earth in the future. And what size would it be? How dangerous is this? To date, very few impacts on the Earth have been predicted in advance because we just haven't seen those objects. There's just a handful that we've actually known about in advance, and hopefully Rubin can change that. Of course, a lot of what the work at UW is on the algorithms, the software. This telescope is being built in Chile, and the formal end of construction is in 1 week. As you might guess, we're very close to done with everything. Not we're done with a lot. And there will be improving many things from here on out. But a lot of the work here is on the algorithms that actually link the, when you see an asteroid, it's a dot on an image. And the way that it becomes an asteroid to us is by seeing those dots moving over time and linking that together and then calculating from all those linkages the orbits that could be physical and then seeing if we can see those again and vetting those fitted orbits over time. And it takes quite a lot of work to turn dots on an image into trajectories through space along with the light curves and even being able to then figure out things about their rotations and properties over time. And with all of that, we can use Rubin to really drill down and get the best science we can and find these really rare events out of the entire sky that we're observing all the time. So what I'd like to wrap up on is how Rubin is available to all of you, in fact. So our first data preview, DP1, is publicly available, and it's available to anyone with data rights. Now, that is a complicated word. What is data rights? Well, in this case, it's anyone associated with one of the universities that has partnered with Rubin, or a citizen of the US or Chile. So many people here can log in and get an account at the website there at the top and actually access our initial data from what we call Data Preview 1. That was made with our commissioning camera just about this time last year. So it was a smaller camera, but using the 8-meter mirror and our mount and testing out our systems. And in the future, the data from Rubin will also be available in this platform to the public and to scientists worldwide. We have currently many thousands of in-kind contributors who have access to the data and will be working on the science as it comes through. And we're getting feedback already from the early people who are working with us and trading their effort to help improve our work by getting to also have access to those images at an early point. And I look forward to more of the data becoming public, and very soon, the data that we take during the night will be public within about 3 days. So at UW, we really focus on the alert production team. So this is the notifying the world about all the things that change. And from that, we will be releasing those images after just about 3 days. And all of that would be available through this platform in a few months. And that'll be available to anyone with data rights. So I'm looking forward to that. And that is everything. So thank you all very much for coming. Question over there first.
With Rubin in the southern hemisphere, it's only hitting half the sky. Is
So there was at one point, and here I'll relate a story Željko, our construction director, related, of that about 10 years ago, there was a group of Russian oligarchs who were planning to fund this in the Northern Hemisphere. And they were in contact with him, and they disappeared. And he never heard from them again. So, no. Yes.
When you showed the image, it looked like there was a big missing spot.
Oh, which image?
When it showed the sky coverage.
Oh, yeah.
Time lapse over.
Yes.
Yeah, there's a big missing chunk. Why is it missing?
There's different parts that are missing. So part of it is because that was a simulation of a specific day, and there was the moon. And so we have to avoid the moon because stray light from the moon will actually set our detectors on fire. So we can't do that. Even pointing at Jupiter would set our detectors on fire. You have to be very careful when you have an 8-meter mirror because it focuses a lot of power.
So do you make sure airplanes don't fly over at night?
We ask for people to respect our airspace, but I have seen airplane trails through our images, and satellites and satellite constellations are an entire other topic that I think has been brought here at Astronomy on Tap in the past, because that's a problem. Yeah.
I have two questions. First one is, I'm a proud owner of the star thanks to the international star industry.
Yep.
Can I find my star if I get access to the data?
Is it in the southern hemisphere?
That I don't know. Find out. But the second question, which is more serious, is obviously there's an incredible amount of calculations that go into this, but where does machine learning AI come into play on future enhancements? Where you have the data,
Mm-hmm.
what do you expect the role of AI in interpreting that
Mm-hmm.
moving forward?
So what I have seen best demonstrated for the role of AI is identifying the things that haven't been seen before. So digging through the vast quantities of data, and from all of that, picking out things that don't match any previous types of classified objects. So identifying things that might be of scientific interest because we don't know what they are. So we'll have classified quasars, and we'll have some idea of what a quasar is and what it looks like in our data. But if there was something that was unusual like a quasar but in a different way, that would be a good type of application for a machine learning algorithm to identify and find and point out, this is like things you've seen before, but it doesn't match any of the observations you've made of quasars in the past, for example. And so that is one application. Internally, we are using AI and machine learning for identifying junk in our data. When we're subtracting off templates, and it's going to be under different conditions of atmosphere, and sometimes it doesn't subtract off cleanly, and AI is pretty good at identifying things that look like they actually was a difference in brightness as opposed to just we messed up the subtraction. Way in the back.
Just kind of a two-part question. You said 10 terabytes of data a night?
Yeah, 10 terabytes of images a night.
Images a night. Are those, so first question is are those saved locally? Do they go directly into the cloud? How are they managed? And then you said power by batteries.
Yep.
How does that system work? If you could explain a little bit more.
Okay, so with the first question, Back when Rubin was getting started, a very forward-thinking person secured rights to help fund a dedicated fiber link from La Serena to the United States. And so we have our own fiber. And from the United States, then the data is transferred to the Bay Area at SLAC, where we have our major data facility. And that data transfer from the summit to Bay Area takes about 15 seconds. At the time I started this project, which is a while back, people were very impressed at telling me that they were doing the data rate of about Netflix. That is no longer the case, but at one point it was the data rate of Netflix. You had another question about the power. So we have commercial power lines that go up the mountain. They supply the power banks. There's a series of 3 different backup generators that run off of diesel that power it when, and the power does go down frequently. And then the diesel generators kick in and take over and power up the capacitor banks. Yeah.
So when you're doing a simulation, I always imagine just sort of raster the whole sky, like picture. So when you're doing a simulation, it's like hopping all over the place, like a random walk.
Yes.
And what is the rationale for that?
Well, the rationale is because we're trying to survey the entire sky, we want to emphasize all of those different science areas. And I mentioned weak lensing earlier, and they really care about systematics. Like when you see something, they want to have seen the same region of sky under all kinds of different rotations, all kinds of different dithering. And so this is actually another application of machine learning, which goes into our survey strategy. So we have weights for different science programs and different regions of the sky, and different regions of the sky will give a different weight to the different ones, and so it programmatically, and it will update during the night based on cloud cover and everything else, where and how it is going to survey and fill it in.
Is it also like, this is an interesting thing 2 years ago, so therefore look at that?
Yes, then we exercised that over the summer, where there was a gravitational wave candidate. There was a gravitational wave candidate, and we received that alert. So we went and we pointed at that area, and we found some candidates for that. And so we did exercise that already, even over the summer. There's a little note out about it, but it's not that exciting yet. Way in the back. So the nice thing about so we can see the ecliptic plane. And the nice thing is the Earth rotates around and is off axis. So we see the asteroids. And if there is something that's going in a wider arc, then we'll see it on the other side. Did I miss anything on that? Okay. Yeah, so we should see all of the asteroids. I saw you first.
Yeah. Is the Department of Energy worried about you finding, like, spy satellites, UFOs, stuff you shouldn't see?
No comment. We delay our images by 80 hours. 80? For release to the public. Yes. Right. So when we take an image, we subtract off what we think the template was. The question was, how do you go from different detections on the sky to linking them together to a three-dimensional orbit in the solar system. And so we find all of the things that have changed. If it's an asteroid, that is almost always a change because it wasn't there before. Then we take all of those changes, and in a huge compute job, we've worked out, well, this change could be associated with that. That is one tracklet, and we're going from the same night, and that could be one part of a vector, and we'll build up this whole catalog of tracklets from multiple observations on the same night. And then we take all of those tracklets and see how could they all possibly fit into different orbits in the solar system. And we filter out everything that could be unphysical and ones that are linked in higher probability with other tracklets, and just sort of filter it on down and end up, it works remarkably well. That's very much what Jake and another Ari is working on at UW. Other questions? I think that's probably good on time, so thank you all once more. There you go.
All right. Thanks so much, Ian. Let's give him another round of applause. All right. Well, thank you all for coming out to our 100th edition of Astronomy on Tap Seattle. It's been a great time here, and our next Astronomy on Tap is still here. Bickerson's is currently closed for daily operations, but they're still honoring events that are going on, so we will be here still next month on October 22nd, and our speaker will be former NASA astronaut Ed Lu. It'll be a great time. I hope to see you all there. Get home safely.